I'm going to go ahead and start the presentation. We'll go through this and then we'll do a little Q&A at the end. Try to get the whole thing in about a half an hour here. We're going to be taking a look at screw conveyors, shafted versus shaftless. Key features are complete enclosure. A little hard to do on a belt conveyor, can be done, but with odor control concerns nowadays, screw conveyors are kind of a natural at keeping spilling and odor contained. Good for congested locations, more compact than belt conveyors, more flexible in design, easier in transition points. You can hard connect one conveyor straight to another, whereas you're going to have to do a gravity drop on belts. They can handle high temperature, higher than a belt certainly, and a wide variety of product and a wide capacity range. Also, they're better distribution when you've got multiple drop points, when you can use gates rather than plows on a belt conveyor. It's just an easier method of distributing product. We're going to look at a couple. These are some very simple, basic layouts for conveyors. Screw conveyors, horizontal, straight incline, and methods of distribution off of these conveyors. You've got, of course, slide gates, but on this one you can see this is a bifurcated chute with a valve. If we've got enough height distance where we can separate with the discharges with a split discharge and a motorized valve here, we can save a conveyor by doing that. And that's often done to split into two separate conveyors for redundant systems. Here's a horizontal to incline. Of course, we can pick up from multiple inlet points on screw conveyors. This is a gravity drop into an incline, so we can do that on a shafted screw conveyor. We can do that on a shaftless also. But on a shaftless, you can do a direct push into a pull without this gravity drop point here. Here we've got multiple gates for truck loadouts, typical automated gates, and you'll see this one is coming up to a pulling conveyor here, and most of you are aware that we'll have a gate, and then the last discharge point will be open, so that we don't have a operator error by closing all gates. We automate gates, but we can also automate the conveyors. This is a pivoting conveyor here on a pedestal. This is the inlet chute right over the pivot point, and we can convey in this direction and discharge here while we're pivoting the entire conveyor. Then we reverse the motor, come out the other side, and load another dumpster on this side. This is also an automated system. This is a stacker, radial stacker, or tail pivot conveyor. This is the pivot point in the inlet chute. These are motorized wheels here, and depending on what your dimension between pivot point and wheels are here, you can get quite a larger radius. And this is typically when you're stacking product in a storage yard, and you can go up to 370 degrees, or 270 degrees on your product pile here. We can also put a compacting head on screw conveyors. This is for screenings, wet screenings, and a compacting head. This would get you a conveyor and screenings compaction with one drive unit. So it's not quite the dry solids that you would get off of some of the snorkel type compactors that specifically built for compaction, but this is a good low cost unit to get multiple 2 or 3 inlets from screens here and a compaction head. We also do grit screws. This is a submerged grit screw here, and then we can typically do a drive up above the wet well with a chain drive. Can do a shaft drive with a 90-degree submerged box, and we can even do a underwater hydraulic motor. Chain drive is the typical on that though. I might add that on the submerged Those can be done in both shafted and shaftless. We're going to talk a little bit about conveyor basics for both through types, and most of those basics relate to both shaftless and shafted. And for most of you are familiar with the difference between shafted and shaftless, but let's take a quick look at a shafted conveyor. Of course, has a shaft that holds the flighting up off the trough. So there's a clearance between the flighting and the trough, typically a ½ inch. So a 12-inch diameter screw is going to have a 13-inch trough inside diameter. This one happens to have, looks like it has some liner in it. Not always typical, but sometimes there are liners in shafted screws. So shafted screws does not touch the liner. The shaft is held up on each end by bearings, a tail bearing, and the drive on the drive end, either pillow block bearings, or even sometimes now we're going to direct bypassing pillow blocks and using flange mount bearings on the trough end plates and going directly into the SCW reducer. Shafted screw conveyors, every 10 to 12 feet will need hanger bearings to hold up the shaft, or the deflection in the shaft becomes too great. And you can barely see in this photograph, there are some lubricators with grease, spring-loaded lubricators that will automatically lubricate that hanger bearing that's every 10 to 12 feet. The shaftless screw conveyor is basically a spiral or a helix without a center shaft. Because it doesn't have a center shaft, it lays in the bottom of the trough, and the plastic UHMW liner becomes the bearing surface. The shaftless screw is only connected at the drive in. At the non-drive in, it's completely free. No shaft, no hanger bearings, no tail end bearings. Of course, it is connected on the drive in. So if we go back and look at the cross section here, I've got a cross section of the shaftless screw with a liner. And because we don't have that center shaft, shaftless screws are typically designed anywhere between, typically between 35 and 50% fill rate. I'd say 35, 40% most common. Knew exactly what your product stream was. You could run this thing 100% if you design it that way. Of course, in our business, we don't usually have that luxury of knowing exactly what our flow is going to be. On a shafted conveyor, our fill rate's typically designed at 15 to 30%. And why is it so low? It's because of those hanger bearings. We don't want to get product in the hanger bearings every 10 to 12 feet. Now, the exception to that is if you've got a 10-foot conveyor and you don't need a hanger bearing, you can go up higher on that fill rate. Or we can go 20 feet plus without a hanger bearing if we design the shaft to handle that load without deflecting too much. Let's just say this is a 12-inch diameter screw for a talking point. That typically has a 2 to 2.5 inch pipe shaft. If we're going to try to design this for 20 or 30 feet, that pipe shaft may go up to 6 or 8 inches. Then we're left with just a few inches of flighting as a carrying face. So there's downsizes to try to eliminate the hanger bearing on a long screw. This is something we also run into on shafted live bottom bends. We have a limit of probably about 30 feet on a live bottom shafted screw because of that shaft deflection. So going back to typicals on conveyors, fill rate's going to be 15 to 30% depending on shaft size. So another basic that applies to both shafted and shaftless is pitch and diameter. And for talking points, this is a 12-inch screw. A 12-inch diameter screw is going to typically have a 12-inch pitch between flight to flight, 1-to-1 ratio. So probably 90% of the screws are going to be 1-to-1. And for talking points, I threw up a 1/2-inch pitch. It's going to carry half the material. And the basics is we're calculating, when we're sizing a screw, we're calculating the surface area of the face of each flight, the diameter, the pitch, trough fill rate, and the RPM all come into play when we're sizing a screw. One pitch that's 12 inches is going to move product 12 inches per 1 revolution. So if you've got a 10 RPM screw, you're going to, at 12-inch pitch, you're going to move 10 feet per minute, as opposed to half of that with a 1/2 inch, with a 1/2 pitch there. So what do we need from you guys to size screws? We need, what is the product? Sludge, screenings, grit, macerated screenings, raw screenings. How wet is the sludge? We need density, and we need design load. And we need the density to calculate horsepower, and we need to be able to calculate volume for fill rate and sizing. So we'll take a quick look at shafted conveyors. They can run at higher RPMs. Of course, a shaftless can run at high RPMs, but you try to hold the RPMs down to minimize the liner wear. And because the shafted doesn't have a liner, there's no liner to change. This liner in here, actually that's not a liner. You do see, that's a different color of the stainless. You do see liners sometimes specified in shafted. It's not required, and you will not get liner wear. You'll get edge wear on the flighting, but you won't get liner wear because it's not in contact. Shafted can run dry without wear, meaning wear on the trough or the flight edge, where if you're running a shaftless dry, there is that contact and friction and wear. Longer conveyors are possible with shafted. There is a practical length that are limits on shaftless because of the compression of the spiral or elongation of the spiral, depending on which direction you're moving in. But with multiple hanger bearings and on the shaft, on the shafted, you can go hundreds of feet with shafted conveyor. They're also very good on live bottoms, just because there are more things you can do with pitch and diameter on a shafted. You can vary the pitch, you can vary the diameter, pull sludge from, do different things with the sludge inside the hopper that you can't do on a shaftless for live bottoms. So on a shafted, and they're not really that big of cons, but you may say that the lower trough fill rate is a con. You may have to size up one size on a shafted sometimes, that you could go a little bit smaller screw on a shaftless. The intermediate hanger bearings and end bearings, they are maintenance points. Limited lengths on live bottoms, we touched on that. Generally higher capital cost, I would say that depends on the spec. Generally, shafted and shaftless are pretty close in cost. Another con is not suited for stringy product, which is specifically talking about screenings here. If you've got a shafted screw in screenings, screenings will rag around this shaft and rag around your drive shaft. It eventually will cause a problem if it's not cleaned out. Shaftless conveyor. High trough fill rates are possible. Low RPM. Typically you're going to have lower RPM because you have a higher fill rate. Ideal for sticky, stringy, wet, lumpy product, and specifically screenings. If you've got a screenings conveyor and use a shaftless and you're pushing away from the drive, you will not get this conveyor clogged up. It will move the product out and into the next conveyor. The UHMW PE liner is the main surface bearing wear item. Some people consider this a pro and a con because they eventually will have to be changed. Another pro, no non-drive-in or hanger bearings. Only the gear reducer bearings are used. Direct connect on non-drive-in. That means we can push into a pulling conveyor directly without a gravity drop point. On the cons, the liner may be difficult to change in some applications if you're hanging from a ceiling, if it's in a light bottom bin and a hopper. I will have to say that very low wear in hoppers, because you're typically going only less than 10 RPM, and it's typically not being run 100% of the time. Long or high volume applications require substantial spiral reinforcement. Because of the shape of the screw, and it's very beefy, it's typically 1 inch thick, 3/4 to 1 inch thick depending on the diameter. It's a heavy spiral, but because of the shape, it's very flexible. And when you're in the pushing direction on this spiral, it wants to compress like a spring, and when you're pulling, it wants to elongate. So we have to do spiral strength calculations to see what that movement is going to be. If it's a large volume or a long conveyor, we may have to back a portion of the spiral with another spiral that may be 2 inches thick near the drive-in. So when you get up to over 50 feet, I'd say we start taking a serious look at the strength of that spiral and look at reinforcements. We'll take a quick look at conveyors by product. And if we look at the columns here, I've got dewatered sludge, shafted, and shaftless. And of course, both of these screws are good with dewatered sludge. I'd say our product line, we probably use 50% of each. We use shafted and shaftless all the time in these applications. We like to go vertical. We like to go shaftless if we go vertical, but we also have done shafted on vertical. So a lot of times this comes down to owner preference. On dried sludge, this is typically either coming out of a greenhouse or hothouse or a dryer. Most dryer applications, it's coming out a little bit too hot for a shaftless and the plastic liner. We stick to shafted screws on dry product. Also, because of the abrasion on the shaftless screw liner, we could go to hard ox bar metal liners, but the preference here is shafted. Wet screenings off of a bar screen, shaftless is by far the best way to go, just because of what we talked about earlier, pushing it away from your inlet to your discharge point. You will not get ragging on the shaft. There's no shaft. I have seen shafted used, and it will eventually rag up on the shaft, and I have seen shaftless used in a pulling condition, sometimes just because they could not possibly push it because of placement, but it too will eventually rag because you're pulling toward the drive shaft if you're doing a pulling. Compacted screenings, again, for the same reasons, shaftless over shafted is the best. The exception to that is macerated screenings, when you've got going through a grinder upstream of the bar screen or upstream of the conveyor. A lot of times you'll have the grinder on top of the compactor dumping into a conveyor. In that case, a shafted is acceptable along with the shaftless. On submerged grit, both shafted and shaftless work well. We would go to a AR-235 flight and our hard face flights on the shafted. We would go to metal liners on the shaftless, and that's hard ox bars, typically about 1/2 by 1.5 inch bars, 4 to 5 bars running parallel to the screw in a trough, and that grit builds up between the bars, and the spiral typically only touches 2 of those bars when it's in motion and it rides on that bed of the grit. So the hard ox bars are about 360 Brunel. The spiral is 220 Brunel. So in that case, you're spiral is your wear item, not the liners. But we slow that down to 10 RPM or slower, and those spirals hold up pretty well in that application. Same with dewatered grit. We would do the same situation with hard-faced on shafted and hard oxbar liners on the shaftless. So both of those screws work well in grit. You got any questions? Okay, no questions. Thank you guys for tuning in, and I appreciate it.